So hi students, today I want to discuss about isomorphism topic in BMS. So isomorphism. So here there are two types of graphs are available. One is a G and other one is a G dash. So G has vertices, collection of vertices and edges, and G dash is also have collection of vertices and edges. Okay, so by looking these two graphs are different but those are same. Okay, now these types of graphs are called as isomorphism. Okay, now so Z is a graph which contains number of vertices and number of edges. G dash is also a graph which contains number of vertices V dash and edges E dash. Okay, for example, if there are two graphs G and G dash, and if the number of vertices, for example, if A and B are the two vertices of G, A and B are two vertices of G, then A dash or A comma B belongs to edge E. So once there is a edge between, if there are two vertices set, if there is an edge between A to B is present in G, okay, in the similar way, there is a function from f of A comma f of B is a set is belongs to E dash. If there is an edge present in G, similar edge is present in G dash, then these two graphs are called isomorphic graphs. Okay, so similar way here we can have three important points. First point is, if there is a function f from V to V dash, then it is known as isomorphic graph. So here first one is, there is a function from V to V dash, so that is 1-to-1 correspondence. There is a 1-to-1 correspondence between their vertices and edges, So 1-to-1 correspondence between their vertices and edges is the first point. And the second point, their adjacency matrix is same. Their adjacency matrix is same. Then those two graphs are called as isomorphic graphs. Okay, for example, here there are two graphs G and G dash. So first of all we have to find out 1-to-1 correspondence between their vertices. So how it is possible with, there is a function from V to V dash. So vertex of original graph G is mapping with vertex of second graph G dash. Okay, now so we have to map like that. Okay, here I am taking the first vertex A is mapping with P with the second graph. Why I am taking this vertex is because, can you observe that each and every vertex degree is 3 in G and also G dash. Okay, now each and every vertex degree is 3 in G and G dash. So we can map with any vertex of G with any other vertex of G dash. So here I am taking, there is a function f from A is mapping with P. Okay, A is mapping with P. Similar way here, A is having a connection from A to B, A to H and A to D. Okay, na? A to B. So here I can place there is a line from P to Q. Okay, P to Q. P to Q means here A to B, and here P to Q means I can map with the B is mapping with the Q. So second one is B is mapping with the Q. So similar way, likewise we need to write all the vertices of original graph G. So likewise we can write all the vertices of original graph G. So now, and you can also observe that a square is inside the another square, right? A square is present inside the another square. In the similar way we can observe that in the second graph also. So here one square is present, right? Okay now, so by looking like this also we can map with these two vertices. Okay now, or here I am mapping AB as PQ. So PQ AB. So not this circle. So here we are taking the above square. Okay now. So above square is mapping with A to B as P to Q, and similar way B to C as Q to V. So C as V. Okay now. So A to B, B to C, P to Q, Q to V, and V to U. Okay, means C to D. C to D means here V to U. So D is mapped with U. Okay na? And next similar way, another square is also there, and which is having a connection. So from P, only we can see from P. So from P we have two connections are over, right? Only one remaining. And similar way for A, already two connections are over. A to B is over and A to D is over, and only one remaining. So simply we can map H with W. H with W. So from that onwards we can map any vertex. So here H to G means W to T. Is it right or not? And once we have to check another connection also. If you are placing H to W and this line is over, right? A to H is over, and means P to W is over. And from W, from H, there is another two connections E and G. So we can map with W is connected with T and R. So simply we can take T as E and G as R. G as R. So remaining is F is S. Okay now. So likewise we have to connect all the vertices one by one. So there is a one-to-one correspondence function from vertex to vertex, V to V. Okay now. And by using this, whether your mapping is correct or not, that can be done in the second step. Okay now. So by observing the second step, whether it is isomorphic or not, by easily we can say that. So one-to-one correspondence between their edges. One-to-one correspondence between their edges. So first of all, write down all the edges. So here original graph A to B, A to H. So likewise vertices. So here each and every vertex edges must be present here. Okay, write down all the edges in the original graph G. So that is A to B, A to H, and A to D. Next B to G, B to C, C to D, then D to E, E to F, F to G, G to H, and H to E. So whatever the edges are present in the original graph G, so write down all the edges. Write down all the edges. So here already we are mapping with A to P, right? So here A is mapping with P, B is mapping with Q. So P comma Q. Similar way, A is mapping with P and H is mapping with W. H is mapping with W. Okay now. So once we are providing A comma B in the original graph G, whatever the vertices we are mapping in one-to-one correspondence, by using this one-to-one correspondence we can write the number of edges also. So likewise P comma Q. Once we are writing P comma Q in the one-to-one correspondence means compulsory there has to be edge present between P to Q. Okay now, that is present, right? And similar way, A and H is an edge in the original graph G. So A is mapping with P, H is mapping with W. So P comma W edge is also present in G dash, right? Okay, next P comma D. D is mapping with U. P is mapping with U. So P comma U. So here U, it is U. So there is a edge from P to U. So here it is also same. Likewise B to G. B to G means Q to B is mapping with the Q, G is mapping with R. So compulsory Q to R there is an edge present. Is it right? Next, B is mapping with the Q, C is mapping with V. So C is mapping with V means Q to V is edge is also present. Q to V is also present. So next, C means C is mapping with V, F. So F is mapping with S. So there should be present a line from V to S. And similar way C to D. So V comma D is mapping with U, right? So compulsory V to U is also present. So this edge is also right. And similar way D to E. D is mapping with U, E is mapping with T. So compulsory there is a line from U to T. U to T is present. Right. Next E to F. E is mapping with T. F is mapping with S. So compulsory here also T to S is present. Right. Likewise F is mapping with S. G is mapping with R. So S to R is also present. So it is also correct edge. Right. Next G is mapping with R and H is mapping with W. Right. So R to W is also edge is present in the graph G dash. And the last one is H is mapping with W and E is mapping with T. So there is an edge from W to T. So here every edge present in a G is mapping with G dash. Okay now. So one-to-one correspondence of their vertices and one-to-one correspondence between edges is mapping is done, right? Once these two are over, then we can write the second point as adjacency matrix. Okay, by using this we can write adjacency matrix. Okay now. So now we can write the adjacency matrix. So here adjacency matrix. Suppose if you want to write the adjacency matrix, first we have to identify how many vertices are there. In the original graph, how many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 vertices. So obviously we can get 8 by 8 matrix. Okay, now we can get 8 by 8 matrix. That is A, B, C, D, E, F, G, H. Similar way A, B, C, D, E, F, G, H. Okay, adjacency matrix for graph G. Adjacency matrix for graph G. So is there any self loops for every vertex? If there is an edge from one vertex to another vertex, then we can provide 1 in the given matrix. Okay, if there is no adjacent, means if these two are non-adjacent, then we can provide 0. Okay na? So who are non-adjacent, we can provide 0, and who are adjacent, then we can provide 1. So A to A, no edge, B to B, no edge, C to C, no edge, D to D. So self loops are not allowed here, not there in the graph. So that's why we can place 0 for all diagonal elements. Okay, now 0 for all diagonal elements. And we can see the graph. So there is a line from, there is an edge from A to B. Right, there is an edge from A to B. So we can provide 1. And edge from A to H. Next A to D. Then remaining all are 0. Means there is no connection from A. And next coming to B. So B to A is already there is a connection, right? So see the graph. A to B means there is a connection from B to A also, right? So 1 minute, I will draw the graph here. So here A is connected with B, H, D. Okay na? So in that places we are providing 1, remaining all are zeros. Next from B. B is connected with A, G, C. A, G, C. And remaining all are zeros. Next, C is connected with F, D, B. So B, D, F. C is connected with B, D, F. So remaining all are zeros. Okay now. Next D. D is mapped with A, C, E. A, C, E. And remaining all are zeros. Okay. Next E. E is mapped with H, D, F. D, F, H. So remaining all are zeros. And next F is mapped with E, G, C. Okay na? G, E, C. Means C, E, G. C, E, G. Remaining all are zeros. And similar way G. G is mapped with B, H, F. B, H, F. So remaining all are zeros. 1. Next last one is H. H is mapped with A, G, E. A, G, E. So remaining all are zeros. Okay now. So this is the adjacency matrix for given graph G. Okay, adjacency matrix for given graph G. Similar way we need to write adjacency matrix for G dash also. So adjacency matrix for G dash. So here adjacency matrix for G dash, before writing adjacency matrix for G dash, first of all, how many vertices are there? Total 8 vertices are there, but 8 are mapped with different, right? So like A, B, C, D, E, F, G, H, we need to write whatever the mapping vertices are there. So write as usual, that is P, Q, V, U, T, S, R and W. Similar way P, Q, V, U, T, S, R and W. R and W. Okay na? So in this manner we need to write. Okay, so P to P, is there any connection? No. P to Q, 1. P to U, 1. P to W, 1. So remaining all are zeros. So 1, 2, 3, 4, 5, 6, 7 and 8. Next Q. Q is connected with the P, R and V. And next V. V is connected with U, Q, S. So remaining all are zeros. And U is mapped with P, T, V. Remaining all are zeros. Next T is mapped with U, T to W, T to S. So remaining has to be zeros. Next S is mapped with T, R, V. So remaining zeros. Next R is mapped with Q, W, S. So remain W is mapped with T, with R, with P. So remaining all are zeros. So this is the adjacency matrix for G dash. Okay. So these are the adjacency matrix G dash, and this is adjacency matrix for G. So is both are same or not? We can observe it. Is both are same or not? Okay, first 0 1 0 1 0 0 1. Next 1 0 1 0. I mean 0 0 1 0. Next 0 1 0 1 0 1 0 0. Right? 1 0 1 0 1 0 0. 0 0 1 0 1 0 1. And 0 0 1 0 1 0 1 0. 0 1 0 0 1 0 1. 1 0 0 1 0 1 0. Okay na? So by observing their 1 to 1 correspondence is same. Okay na? So 1 to 1 correspondence is over. Okay. Next their adjacency matrix is also same. So by observing these 2 points, we can say that the above 2 graphs are isomorphic graphs. Okay na? The above 2 graphs are, therefore we observed that there is 1 to 1 correspondence between vertices and edges. Okay, and similar way their adjacency matrix is also same. Then these two are called as isomorphic graphs. Understood? Thank you.